I'm going to continue the theme of presenting educational information. So you've probably seen our 3D models before. We have them at the table at our booth, of course, and you've probably seen me speak about them before when we started making them initially. And there's been a few new changes in the technology, updates, and new things that we're doing. So I'd just like to share with you what those are in case you're interested in doing 3D prints yourself or working with the library and having us do some 3D prints for you. I'd like to start by acknowledging the Geological Survey of Canada. Without their funding of this geologic model, we wouldn't have anything to be printing. So it's based on well files at the library and other geological data sources. Different borehole databases and bedrock surface databases have been put together in the 54-layer model of Ontario's lithostratigraphy, which is what a lot of our models are based on. And we also have new models based on the hydrostratigraphy. And of course, without the help of other organizations like the Ontario Geological Survey, the Ministry of Natural Resources and Forestry, or Ministry of Natural Resources now, and the petroleum industry members, we also wouldn't have the funding or personnel available to do this work. And I'd also like to thank the educators that we've been working with to present these models in the classrooms, both high school and university classrooms, and to figure out how best to use these models with students to make an impact in Ontario. And I was just told yesterday on the golf course that my new job will be visiting schools 4 days a week and letting them know that we have oil here in Ontario. So why do we do models in the first place? So comprehension is the first key point. It's extremely easy to pick up a model, just look at it, rotate it around in your hand, and you instantly understand what the shape and the geometry of the geological layers is. 3D software on a computer is quite good, but you do need to be a little bit experienced to use that. You probably need to have a special license. Even if it's free, you might need a registered account. In education, we can take these models into schools. They're portable. They don't require any power, any setup. Again, they don't require a license. We don't need to install software before we go there. It's easy. Outreach, we can come to events like this. We can share the models at our table. We can go to community events, or you can take your own models to community events, share them with people quite easily. So what is 3D printing not? Well, 3D printing is not just a simple one button and you get a nice model. Usually, you just get kind of a mess if you don't set it up properly. So how does it all start? Some of you might remember this slide from some years ago. You start by having data in a GIS system that's geographic data, and that data has a value. It can be elevation, it can be depth, it can be thickness, it can be temperature or pressure. Any gradient that you have over an area, that's a 3D model, and we can convert that into a print. So we start with a program like Leapfrog Works, which is what we use with the Geological Survey to create the Geological Survey used that to create the model of Ontario. We can also use Blender, the 3D modeling and animating software, to create these models. You can make it from GIS, so anywhere where you can make a 2D surface that's a gradient surface, we can turn that into a model. And then we usually take the model from those softwares and bring it into Blender, which is a 3D modeling software, and we turn it into more of a map or cartographic element. Because what we have is just a plain model to start, but we need to be able to assemble that somehow. So we add pegs or some other kind of implements that let us put the pieces together. And of course, without a title, we wouldn't know what we were looking at. Without a scale bar, we wouldn't really have a clue about how large this thing is in real life, because we're not printing Ontario one-to-one. And without these other labels and convenient things, it'd be more difficult to use the model. And so we create a model that's a lot more like a map in the cartographic sense, and you can use that as a tool to understand what it is that you're looking at. There's two main ways that we're doing models at the library. The first is the SLA or resin, which is on the right-hand side of the screen there. Those were the first models that we created, and they worked out pretty well for us, but there were some drawbacks to that, which I'll go through in a little bit. And eventually we transitioned into making FDM models, which is the gray one you see there on the left side of your screen, which was found to be a little bit better in certain areas, particularly cost and ease of use. But as you see, there are trade-offs. So the resin model, the lower one there, is quite a bit higher resolution. The FDM model, the upper one, definitely the resolution is missing and we can't do the labels in the same way. There are ways around this, of course. We can just do the labels in a different way, do them a little bit larger. The trade-off that makes the resin not quite as good, in our view, is that the model turned out to be quite brittle. Some of the pieces were quite thin, and when they were dropped, they would shatter. And also the cost is much higher, which makes it more difficult to distribute in classroom settings. Once you have your model completely done and ready to go, you bring it into what's called a print slicing software. So here you can see one plate of our hydrostratigraphic models, the aquifer units being prepared for the printer. And just this one plate here, the software generates 6.5 million lines of instructions for the printer to run. So it is pretty complicated. And you do get a lot of choice over how you're printing, what speed you're printing at. We found that printing much slower than the default speeds, even slower than the fine default speeds, and lowering the acceleration quite a bit, improved the print quality quite drastically, and gave us much better quality prints in the FDM. And then you have choices about how you're going to support your model and other kind of mechanical things, because you can't just have this thing appear in midair, so you have to think about how to orient it and support it as it prints up, and then how thick are your lines going to be, how large of a nozzle are you going to use. It all contributes to your final resolution in the end. And here's what two pieces look like when they just come out of the printer. So you can see we've had to create that support or direct the software on how we want the supports to be created, what orientation we want to print it in. We want the business side up so we don't have to break any supports off of it, and it has a much neater finish. This was the first model that we created that hopefully you've all seen, the 4-layer model. It had great resolution, and we printed quite a few of them. Of just assembling the 4-layer model. So we had the Precambrian, the Ordovician and Cambrian in one, the blue, the Silurian, and the Devonian. And the main issue with that is that it was expensive and it would shatter when we used it in classrooms. So we printed a smaller, tougher resin model. It was less expensive and more robust, but it was kind of difficult to make, and we had to bake it in an oven for an hour or two at a high temperature. And so it was a little bit complex as well, and it didn't have any color. So we had to color it ourselves by hand. And once again, we made quite a few to use in classrooms. Once we had that, we had the hydrostratigraphic model by the GSC was ready. And so we made that model out of resin to begin with. But once again, we weren't able to color or assemble the layers as easily with the resin material. And so Connor found a way to glue the thin layers together to save the aquifer by combining it with the aquatard and color it using some alcohol-based inks in order to get the hydrochemistry. And then we made one nice model out of resin, a large 98-piece puzzle to use in the classrooms and at events for people to assemble. That's illustrating one of the drawbacks of resin. When you get a little bit of a flaw or a failure, you get spectacular failures. And the resin is nice and sticky and a little bit challenging to work with in the office. But we did get our 98-piece puzzle, and it takes about 12 minutes to assemble. And then we moved on to making other models. So this is a Saskatchewan model. We did it in resin, and then we did a larger one in the FDM. That red piece there that you see is all one big solid piece. So that is one of the key things about moving to the FDM style printer, is that now we can do much larger pieces. So it's about the size of a rock hammer there, which is a great improvement over the other one. Another thing you can do with FDM is you may have noticed that some of the models have more than one color per part. And so the first way that we tackled that was to do something very similar to what you might do in GIS, which is just to use an elevation gradient. So you can actually get filament that has a built-in natural gradient. And so as you print a map, if it's an elevation map, you just naturally get this kind of nice looking gradient on your map. And then of course we did the same one in resin, but you can see we just have one color now per part. One of the other ways besides pegs of putting pieces together, we can put little magnets in them either as they print or after they print. And we did quite a few models, eventually with FDM, multicolor models. And this is one of the first ones we did where you can see that the printer now can actually change colors as you print. You are locked into a set number of colors, up to 16 in total. But now we can have different colors as the model progresses. And so we can do these geology maps that have colored areas for the different rock types. And we can do these other interesting type of maps that are more like a true-to-life color map. And you can see on the right-hand side, we have a true-to-life 3D model of Pingo, which is a formation of frozen ice in the north that's been pushed up by hydraulic pressure. And what we've done here is, because we can only have 16 colors, is we've made a little piece of software that will take an aerial photo or satellite image, and we predefine 16 different colors that are in that image, and the software will convert all of the pixels on that image into one of those 16 colors, whichever one it's most like. And then we can print this photorealistic 16 color model, one little tiny drop of this material at a time in different colors. And you can see, if we zoom in, you can see all the individual little dots. We've broken the model down into 0.2 millimeter dots, and we've had the printer go along and color each one individually. And of course, once we discovered how to do the multicolor models, we printed a lot of them. You can actually have your own if you come to our booth. We have this little tiny version as a keychain if you'd like. And we did it in a slightly larger medium format model with 6 layers. So we added the Cambrian now, and we divided the Ordovician and the Silurian into multiple layers, which lets us see some of the really neat features that I'll get to in a bit. And we did the same for the hydrostratigraphic model. This way, we can have the printer take care of all the work of those different chemical zones on the model, instead of having Connor sit and paint them all by hand. It lets us reproduce a lot more fine detail, and it lets us reproduce it a lot more accurately, and we get a very similar reproduction each time. And we can take that hydrostratigraphic model and we can cut it into smaller areas. So this is just the conservation area around London, Ontario. And so you can see what are the aquifers and aquitards where we are right now. As you spin it around, we can see the fresh water in blue, the sulfur waters in yellow, the brines in orange, and even a little tiny hint of Cambrian at the very bottom. As for the large model, this is the one that we're primarily using in classrooms and in outreach to promote the bedrock geology of Ontario. And when we go out there, these are some of the things that we point out to people that you can see in the model. So first off, you have bedrock. Obviously, as you look straight down on it, you have the different relief and topography of the bedrock and the changing bedrock units as you go from southwest to northeast. That's one of the first things people notice, is that the colors are changing. And if you zoom in on it even more, you see things like, well, the bedrock has these interesting characteristics in it. It has these bedrock valleys. You can see on the left side, there's quite a good one there. And you can also see down by Hamilton, we have the bedrock valley. And of course, by Toronto, you can see the Niagara escarpments quite prominent on the model. And as you dig down through the model, taking off layers, you get to see some of the features of the bedrocks. So this is the top of the Guelph Formation. We decided to cut the model there, of course, because it very famously shows the Guelph Reefs. As you go deeper, there are fewer features and rough spots on the model, but there are still some items of interest. So the rough spots here that you can see, that's the electric and the Dawn fault, and their subsurface faults are still showing all the way to the bottom of the model. When you get to the basement, we can still see some of those faults, but now you can also see the shape of the basin. So we've got the Chatham Sag, the Algonquin Arch, and we can see the basin dipping quite aggressively under Lake Huron and under Lake Erie. And once we've got all that, we can do other neat stuff like link it to digital presentations. So this is a 3D printed model, but it also has an integrated QR code. Most of our models do. And that QR code can link to data hosted online that keeps the model current or provides more ways to interact with the model. In this case, you have your choice of augmented reality version of the model or an animated version of the model that shows year by year what's happening in the model. So how have we actually used them? So we've sent quite a few of these models out into different classrooms for use. We've visited some classrooms to give people an overview, but we're working also with the University of Waterloo and University of Toronto to have some of these models in the classroom, particularly the one you see on the right-hand side, the 4 layer 4-quadrant model that you can break apart and see cross-sectional views of the bedrock geology. So that's used in classes to help students understand how the boreholes can be linked up and how the geometry of the subsurface actually looks. And we're having a speaker tomorrow, John Johnson, tomorrow morning at 9:45, and he's going to tell us how well this has gone over in his classroom. And we also have a larger model that you can see on the left side that we've taken to different events at Western University for GIS days and other outreach events. And it's a puzzle that we challenge people to put together as quickly as they can. And I think the record for non-geologists is 45 seconds. And then Connor's record is, I think, 23 seconds. So challenge him if you dare. And then some of the last things that we've done are to print something really, really large. So we printed this core round Blenheim. It's about 6 feet tall. It has every single layer that was in the model. You can take them all off one by one. You can see a reef. You can see several pools. There's a lot of detail. And we didn't bring that today, but if you want to take it apart, you can come to the library or one of our outreach events. In addition to this model, we're looking at other models to bring to the classroom to help people engage with the subsurface and learn about Ontario's geology. Thank you.